Hello, hello, BC Calculus friends. Today is still March 16th. It's still Bowtie Tuesday. Uh, I'm still your friendly neighborhood math teacher, Mr. Quirk. And I wanted to talk in class today about these notes that I'm sharing with you right now. And as you all know, I can make very short videos. So you're looking at the length of this video and you're like, wow, he made a really short one. It's only 10 minutes long. Isn't that amazing? Um, Differential equations. There's so much to them. We've talked a lot about differential equations for a long time. But in this section with slope fields, there are two other main topics. One is Euler's method, not talking about that right now. The other are the different cases of growth and decay. One of which is, well, they're all super important, but one of them is a BC topic, which makes it especially important for us. So I wanted to talk through these different cases of growth and decay that are possible in the world of AP calculus, okay, and give you some problems to look at on that. Case one, we looked at in class last Thursday, March the 11th, okay? Today's the 16th, right. Maybe I zoom to right here. Case one was that the dy dt equals Kentucky. I think in class I wrote dy dx. But when it comes to growth and decay, the variable t is used more often than even the variable y. The y could be any letter, right? So dy dt equals ky. This is the rate proportional to the amount present. The rate of change of some quantity is proportional to the amount present. Dy dt equals k, the proportionality constant, times y. If I were to solve that differential equation, you would get the solution y equals ce to the kt power. We did the solution in class last Thursday. We filled in the space between here and here, right? This big purple space. Boom. That's where the calculus happens, right? Why is it not writing? Come on. I pushed the button. There it goes. I can fill in this space with calculus, right? I solve the differential equation and dy dt, and I get y equals, okay? If k is negative, then you have exponential decay. If k is positive, you get growth. We talked about that example last week in class. That is the rate of change proportional to the amount present. Rate of change proportional to the amount present. Okay. Notice what's sort of important here is just knowing the differential equation, recognizing the differential equation, and then just automatically knowing the solution. If you see this highlighted in yellow, if you see this differential equation, okay, then you know it's going to fit this solution. You don't even have to do the math. You could memorize that, right? Now, what is it going to normally look like? It might be like dc dt, and that's a bad choice of c. I made it a q. dq dt equals 5q. I didn't want to use c because of the c down below in red. So the rate of change of Dairy Queen is 5 times the amount of Dairy Queen. That's 5q. Okay. So what does that mean? That would mean that q would equal c e to the 5 is k, 5t. And what I would need to do now is solve for c. All I would need to do is plug in some point for t and q, which they're always going to give you an initial point, right? And then you would have the c value. So then you'd have the solution. You really don't even use calculus when it comes to this stuff, okay? You don't have to. If you can memorize the rule, basically, which is also difficult in and of itself. So this other case over here, we need to zip it along. It's possible that the rate of change doesn't change proportional to the amount present, but it changes proportional to the difference between that amount and a fixed constant. Okay? So this is the rate of change. Oh, I thought I was on the highlighter. The rate of change of y. I'm looking at this case 2, letter A. See letter A? The rate of change of y is proportional to the difference between the amount present and the fixed constant. The fixed constant is the number A. Okay? And it turns out with this situation, there are two situations. So case 2 has two parts, A and B. Okay? Notice in part B, the proportionality constant is negative. And you might think, well, how come we didn't have that in part A? Well, we could have had that in part A. It's just when you solve the differential equation in part A, it's the same solution. You just get a negative k. Well, notice here it's a little bit different. Notice the solution to part A is y equals a minus ce to the negative kt. And this is y equals a plus ce to the negative kt. Both of them turn out to have a negative k. Do what? How does that happen? What? Crazy times, right? Why are there two differences? So you see what's happening next might help. If I scroll down, here are the solutions to the differential equations, okay? Over on the left side of the yellow line, we've already done that. We did that in class last week. I solved for y. dy dt equals ky. You move the dt to the other side. You also have to move y back to the left. Then you integrate both sides of the equation. You solve for y. Turns out if k is less than 0, you have exponential decay. If k is greater than 0, you have exponential growth. To the left of the yellow line, that is the exponential law of growth and decay. Your PERT formula, as we called it last year when we did continuously compounding interest, CE to the KT. If k is negative, it's CE to the negative KT, and the graph goes down. Notice on the right side of the yellow line, our case 2 here, the rate of change is not proportional to the amount present. It's proportional to the amount present from a fixed constant. The difference between the amount and a fixed constant. What's actually happening here on the left side of the yellow line are two different versions of decay. Both of these problems are decay, okay? This first example, this part A, is actually what we call negative decay. See, if you look at that graph, it doesn't look like an exponential growth graph, right? The graph here is not like, it's not going up that way. It's going up so that it's still concave down, which is like like an exponential decay curve that's been flipped over. So if you look back at the equation here in red, the red equation, notice it's negative k. Negative k means decay, but it's a negative in front of it, which flips the decay curve over. It's a decay graph that's been flipped over, and then it's been raised up to some limiting value. Two very super easy examples of these examples on the right. This second case of exponential growth and decay. Newton's law of heating and Newton's law of cooling. If you take a frozen piece of, steak, or pot roast or chicken, take a piece of frozen chicken. It's really cold. Its temperature is really low, right? And you put the chicken on your kitchen counter. The chicken is going to heat up to room temperature, which is more warm, right? Hopefully your rooms are warm, right, and not freezing cold, so the chicken stays frozen. Wouldn't that suck, right? So Newton's law of heating, Newton's law of cooling says if you take, and this was what happened with the boiling potato that we talked about in class today. Why is this not undoing? The boiling potato, right? It's really hot. That's up here, hot. But over time, it cools down to room temperature, which is more cool, right? Or should I say warm? like it was before. This is warm. So what's happening here in the black and pink? I solve the differential equations, both of them. You really don't have to know how to do that. You theoretically should know how to do it. You can take the time to look at those on your own if you want at another time. But the, this is really what's most important is that you know the solutions. See, the solutions are highlighted here in the green highlighter. This is the solution to the differential equation. This is a solution to a specific differential equation. This is a solution to a specific differential equation. The differential equations are written up above, right? In the book, it gives examples of these, and I read the ones on the left. I read them in class last week. A colony of bacteria grows proportional to its size. Money invested at interest compounded continuously grows at the PERT formula, which is CE to the KT or PE to the RT, same thing. The concentration of Tylenol in your blood, right? Or Motrin, or I think also use the example coffee, the caffeine that's in coffee, the caffeine that's in a Mountain Dew, right? Over time, the amount of that caffeine in your bloodstream decays at a rate proportional to the existing concentration. Okay. Half-life, right? If you have a bottle of carbon 14, okay, over like, I don't know, 1200 years, you're going to have half of it because it's decayed. It just disappears. It just appears. What's going on the other side? Case two. Advertisers assume the rate at which people hear about a product is proportional to the number of people who haven't heard about it. Oops, heard about it. Heard it. Heard about it. I was trying to write all these down earlier so it would be ready to go and the notes would go quicker. It's already taken too long. This has been at least 10 minutes, hasn't it? Dang it. Newton's law of cooling, also Newton's law of heating. I mentioned both of them earlier a minute ago. It says that a cold object, Newton's law of heating, a cold object will warm proportional to the difference between its temperature and its environment. Because of air friction, the velocity of a falling object approaches a limiting value. So like years ago, you remember when you were a kid, you'd hear like if you drop a penny off the Empire State Building, it'll like go through a person's head on the ground. Okay, well, obviously, if you drop something off the Empire State Building, like a piano, it's going to go through somebody's head, right? But a penny probably won't. It might hurt, but it's not going to go through their head. Years ago, I was at Kentucky. No, I wasn't. Sorry, I was at Kings Island, and we were at the drop zone, the drop tower, whatever that thing's called. And these dudes next to me, they took a stacks of pennies. They had like 5 pennies, and they put them on their knees. And then when the thing drops, the drop tower is like this huge, like 300-foot tall tower, and you're sitting in a chair buckled in, and then it drops you. Well, what was cool was these pennies just like floated in the air because they drop like a half a second after you drop. So the pennies just like float like pretty much at eye level all the way down. Okay, the pennies don't like accelerate with velocity and then impact themselves in the ground. They just go like tink tink tink. Okay, go away. It's annoying. So examples of case two, right? So this is what happens. This is what's most important, guys, right here. You recognize the differential equation. You then know its solution automatically, okay? If you want to solve it by hand, my notes to do that are right here. I'm going to roll past this because there's a third case. And the third case is a BC topic. Logistic growth is a BC topic. Some of you guys are in AP biology, probably. At least one of you has got to be in AP biology. And Mr. Clements has probably talked about J curves and S curves. Notice these graphs here are technically all J curves. But if I take the big red Sharpie, right, this one looks the most like a J, the one on the far left, right? Exponential growth looks most like a J. Exponential decay is like a backwards J. Okay, so negative decay is also like a J, but it's rotated in backwards. And then this regular exponential decay is also a backwards J. These are what are meant by J curves. They kind of have a J shape. An S curve is when you put 1 plus 2 together. What is 1 plus 2? 1 plus 2 is 3. So case 3 is the rate of change of a quantity is proportional to both the amount and the difference between the amount and a fixed constant. It's both case 1 and case 2. Notice it's Kentucky. dy dt equals Kentucky times a minus y. Okay, and so this is what is meant in Mr. Clements' class by an S curve. And if you look like it, it kind of looks like an S curve. So logistic growth starts out exponential. Okay, it looks like exponential growth. And then it flips into what is called negative decay. Okay, it's technically still going up. The slopes of the tangent lines are positive. Okay, but it doesn't fit the definition of growth because the exponent would be negative at that point, right? So it's a decay problem, but it's a decay that's been flipped over. It's been reflected. So it's an exponential growth curve married to, like we saw the Newton's law of heating problem, married to a negative decay curve. So this is an S curve. Logistic growth is dy dt equals Kentucky times a minus y. How do you solve that differential equation? How do I solve this? The one in yellow. See the one that's highlighted in yellow? How do I solve? Oh, don't do that. How do I solve this right here? Well, I have not done that for you on here. I'll put it in the notes. You can look at it if you want. I'm not even going to show you on here. It is an amazing problem. It's not even in the book. The book's like, yeah, you can do it on your own if you like. So I did it on my own. This is the solution. This is what you need to remember. Okay. So notice what's happening with this graph. The graph has a horizontal tangent line at A. A is that limiting value, right? A is the fixed constant. Maybe it's the room temperature, right? Like that we saw in the Newton's law of heating and cooling problems. But what will happen is over time, as time gets bigger and bigger and bigger, your equation is going to get closer and closer and closer to A. And if you think about this equation here, this is listed in the book, so I wrote all these notes here. Think about this fraction. As t gets bigger and bigger and bigger, as t goes to infinity, well, this term's going to go to 0. C e to the negative a k t power will go to 0. Okay? Why is that? Well, if you think about just that term, think about that term by itself. By itself, that is an exponential decay formula. C e to the negative t power. That's right here. C e to the negative t power. And again, k is just some constant, some coefficient. So what we have down here is we have a times k, which is still just a coefficient of t. So this is exponential decay. It gets smaller and smaller and smaller. It goes to 0. What is 1 plus 0? 1 plus 0 goes to 1. So the denominator is going to go to 1, and therefore, what is a divided by 1? A divided by 1 is a. So as t goes to infinity, this equation is going to go towards a. It gets closer and closer to a. Notice at a half of a, very important fact is happening here. At a half of a, the curve switches from, and this is at the y value, right? Half of a, it switches from exponential, it switches from concave up to concave down. It's a point of inflection at some t value, right? That is also the place where the rate of change is happening the most. That is the place where the slope of the tangent line is the steepest, right? How do they say it here? It attains a maximum at y equals a over 2. The rate attains a maximum at a equals y over 2. So if you were asked, like, when would you could solve the equation for t, right? See, if you know a, you're going to know a over 2, so you could solve for t, because a over 2 would be this value, right? That's your y value. So you could solve for the time at which the rate is increasing the most. Okay, so notice the a value. You're going to be given the a value. Okay, this a value will be a part of your differential equation. It's the same a value you have here, and it's the same a value you have here. Okay, examples of logistic growth. Diseases spread through a population P. What are you talking about? Like what's going on right now and has been for the past year of our lives? Diseases spread through a population P at a rate proportional to the number of people infected, which is N, and the number of people not infected. So this is what we were trying to do back in 2 weeks last April. We want to flatten the curve, right? We were wanting this curve to go so we could come back after spring break, right? Well, it's got to hit this. I remember saying this to one of my it was one of my AP calculus classes last year because we had already talked about this stuff. And I said something really rude, like, because nobody really wanted to have to shut down. People were mad about shutting down, and we didn't even realize spring break was going to get canceled. Remember, everybody thought, well, we're going to have 2 weeks where we flatten the curve, then we're going to have spring break, then we come back to school. And I was like, guys, if we don't shut down, we're going to lose a whole lot of grandparents. As it is, we're already going to lose a lot of grandparents. That's what's been happening in Italy. It's been really bad for the elderly population. I was like, so we could shut down and hopefully our grandparents will make it through this, And and it's happened. Like I have had close people that I know that have passed away from COVID-19. I mean, it's terrible, and it doesn't happen in so this is like real life math. You know what I'm saying? Like this isn't just made up stuff to torture you. Uh, the differential equation you see at the very top of the screen, right? I'll highlight it in green. See the green? It's also down here. So n prime is the same thing as dy dt. Ky is the same thing as kn. A minus y is the same thing as p minus n, where p would be the total population, right? Over time, eventually, it's going to get us all, right? So we want to build up the ability to fight it. So we have herd immunity and we have vaccines, right? We get COVID-19 and then we get over it so that we have antibodies, right? So this is a science. A rumor. So I didn't take the time to write this down. A rumor, a fad, or a new religious cult often spreads through a population P according to the formula, which you see written at the very top of the screen, right? Where N is the number of people who have heard the rumor, acquired the fad, or converted to the cult, and P minus N is the number of people who have not, right? Bacteria in a culture. So we talk about bacteria growing exponentially. We talk about humans reproducing exponentially, or rabbits reproducing exponentially, exponential growth, right? The issue is that can only happen if there's enough space for it to happen. So a bacteria in a culture on a petri dish will grow exponentially, but eventually the numbers of bacteria slow down because they reach the limiting factor that is being basically contained by the petri dish, right? There is only enough bread for the mold to grow on, right? If you put a piece of bread on your counter and just let it sit there for weeks, it's going to grow mold, okay? But it's not going to grow where there's not bread, right? It won't grow on your countertop as easily. It's possible, like maybe you left a little bit of jelly on your countertop, and so the mold would eventually spread a little bit. But if you have just a plastic countertop or a rock, granite, quartz, marble, even if it's just like linoleum or what do they make counters out of? Just plastic wrapped counters, right? That we used to have in my kitchen. It's not, mold's not just going to grow on it. It has to have something to grow on. So bacteria in a petri dish, right, grow at a rate proportional to the product of the existing population and the difference between the maximum sustainable population and the existing population. Replace petri dish with fish in a small lake. Ants confined to a small receptacle. Fruit flies supplied with only a limited amount of food. Yeast cells, etc. Right? population of deer in a forest, right? They can't keep growing. There's some limiting value at which they attain a maximum. This is some crazy science right here. I didn't write this one down. I thought I'd read it. In an autocatalytic reaction, a substance changes into a new one at a rate proportional to the product of the amount of the new substance present and the amount of the original substance still unchanged. Okay, so we are talking right here about this product, right? This is the product of the amount. This is the product of the amount present by the amount still unchanged. Okay, y is how much is there. A minus y is the amount that's like there, right? It's the other side of it, right? It's the difference between the total and the amount present. The product is equal to times some proportion, right? Some constant is that rate. So I wrote some of these things down here. You can see that. How do we do this actual problem? Okay, these are what some of the problems look like. Holy crap. I have two of them. One of them I already worked out, but I thought that we'd go through this one together. Exponential growth, decay, logistic growth. Because of a limited food space, a squirrel population cannot exceed 1,000. Oh, bam, right there. I'm thinking about some graph where boop, 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 there's 1,000 squirrels, right? The graph is going to approach some limiting value of 1,000. It grows at a rate proportional to both the existing population and to the attainable additional population. So we are talking about logistic growth. You look for that word and, because we're talking about this much and then the other part, right? They are being producted together. So what do I know right now? If it's logistic growth, the equation is, and I could use any numbers of letters like dy, dy dt or dn dt or n prime, like we did for the number of people that have gotten the virus in that last example. But in this case, we're talking population, so let's just use like dp dt. And what is the differential equation for logistic growth? It's dp dt equals k times p, okay, times the amount, right? Which in this case, the amount like possible is 1,000. That's my A, 1,000 minus P. A equals 1,000. That's what I read from right there. This is my differential equation. I know the A value, the maximum possible attainable population, right? So since I know that differential equation, then I automatically know its solution. What is the solution to this differential equation? The solution is P equals. Now, do you have this memorized yet? No. But you got to stare at these formulas until you have them memorized. It equals A divided by 1 plus C e to the negative A kt. So you see, this is A right here, 1,000. 1,000 is A. See how A is 1,000? That 1,000 also comes down to the numerator here and the exponent of E here. I know that automatically. I know the solution to the differential equation right here. So what's happening with this logistic growth crap is using calculus, but I don't actually have to do calculus. What I have to do is know this formula. Okay? I have to know it. Now, will they ask a question like this on the AP exam? Maybe not. In the Barron's Guide, there are a couple of multiple choice problems that I'm going to put on your homework that that make this all kind of like maybe a little more practical. But we could see a problem like this one, right? Put it in the book here. So what I want to know is, if there were 100 squirrels 2 years ago, 1 year ago, there was 400 squirrels. Notice how they switched the variables around on you. We went from population to time, and then we went time, population. How many squirrels are there now? Okay, so at this point, I could see how you're going, what in the heck is going on? What year is now? What year is it? Is it 2021, or do I go back to when the book was written in 2009? Oh, geez. Okay, it's all relative to now, okay? And remember, with exponential growth and decay, that time is the exponent. And remember, time 0, let's pick a couple other colors. At time 0, the population at time 0 was how many there were in the beginning. We always use 0 time for the beginning amount. So in the beginning of this problem, it was 2 years ago. I'm not going to use -2 as my time. I'm going to use 0 as my time, and there were 100 squirrels. 1 year later was also 1 year ago. Okay, 1 year after the initial time is t equals 1, right? There were 130. No, sorry, that's the next problem. I already did the next problem. Sneak peek. How many squirrels are there now? So what are they asking us to find? They're asking us to find p of 2. That's my goal here. And I can do that very easily. How do I find p of 2? Well, this is p of t right here. Well, all I have to do is plug 2 in. The problem with plugging 2 in is I don't know c and I don't know k. In order to find c and in order to find k, I need to know 2 other points. Oh, what do you know? They gave me an orange one and a purple one, right? So I got to have 2 points. These 2 points are going to help me find c and help me find k. Which one are we going to find first? Well, they're usually always going to give you the amount at time 0. Okay. Start with that point. I don't know what I'm finding first, but I'm going to start with the 0. So I'm going to use orange. Okay. Orange. Plug in 0. For 0 for t. If I plug in 0, what do I get? I would get, well, 1,000 divided by 1 plus c. E, what is negative 1,000 times some number k that I don't know times 0? See, I don't need to know k. I can find c first because this is e to the 0 power. And what is the population at time 0? That's the 100, goes over here. And what is e to the 0? E to the 0 is 1. And c times 1 is c. So what did I do first? I plugged in 0, comma, 100. Now I can solve for c. This is a very simple equation to solve. Cross multiply, right? What's 1,000 divided by 100? 1,000 divided by 100 is 10. Now, how do I get rid of plus 1? I subtract 1. I'm kind of running out of space. I'll just do it this way. 1 plus c equals 10, so c equals 9. What do I know now? I know that the c is 9. I use my orange point. What do I do now? I switch to green. I'm sorry, I switched to purple, right? I'm going to go to purple. I know that there are 400 of these damn squirrels when there can only be a maximum possible of 1,000. At 1 plus 9 e to the negative 1,000 k times 1 power. See, now I'm going to plug 1 in for t. I plug 1 in for t. I plug 400 in for p. Now, do we actually have to solve for k? This is the tricky thing that I actually didn't realize years ago when I first did this problem. I would solve for k, and you'd end up with a natural log. To see how it's e to a k power, you'd have to get the k down, so you hit it with a log. It's base e, so it's a natural log. What I can actually do is I can actually just solve for this whole number. Solve for e to the negative 10,000 k. So how do I do that? Next step, cross multiply. When you cross multiply, you would end up dividing 1,000 by 400. That would equal the 1 plus 9 e to the blah, blah, blah. What would you do now? You would subtract 1 because that gets rid of the plus 1. How do you get rid of timesing by 9? You divide that whole damn thing by 9. I know you guys are tired of this video, and I'm running out of space. So what happens is I would do 1,000 divided by 400, subtract 1, and then divide by 9. And I wrote that here. It's 1/6. You get 1/6. E to the negative 10,000 k is 1/6. If you wanted to solve for k here, you could. If you were asked what is the proportionality constant, what is the proportionality constant of this growth model, you could solve for k. That would be your answer. But what are they wanting us to do? They're wanting us to find p of 2. So now I'm going to switch to green. How do I find p of 2? P of 2 is going to be 1,000 divided by 1 plus 9 e. Nope. Not doing e. What is another name for e to the negative 10,000 k or 1,000 k? E to the negative 1,000 k is 1/6 to the second power because t is 2. Now that's some crazy algebra. None of your algebra / pre-calculus / geometry teachers ever made a substitution like that before. But if you think about going back to the green equation up here, I'm highlighting in yellow. The green equation on the left side, highlighting in yellow. See, what I just found was that this e to the negative 10,000 k is 1/6. So I can just substitute a big old fat 1/6 in there like that. See that? So it's c times 1/6 to the t power. And the t power is 2. 2 represents how many squirrels there are now. 2 years since these squirrels started getting busy, right? How many are there now? Okay, so I can do this even without a calculator. What is 1/6 squared? That's 1/36. What's 1/36 times 9? Well, that would be 9/36. 36. What's 9 over 36? 9 over 36 is 1/4. What's 1/4 plus 1? 1/4 plus 1 is 5/4. What's 1,000 divided by 5/4? Well, that would be the same thing as 1,000 times 4/5. And 5 would go into 1,000 200 times, and 200 times the 4 is 800 damn squirrels. Now, squirrel. Daggone squirrels, they're reproducing like rabbits, aren't they? 800 squirrels. That's some heavy stuff. You might need to go back and watch this again. I love it. Some math there. Okay. Similar problem. You can tell this video is almost over, right? I'm about ready to cut it off. Suppose a flu-like virus is spreading through the population. Holy crap. Can we not? Can we not? Like, are you serious? When they wrote these damn books, they weren't thinking about this actually happening. It's always like, suppose. Well, it's actually happening. And I'm calling this, that we're going to fix this COVID-19, and it's not going to happen for 100 years. So when you guys are 118 years old, you'll be telling your great-great-grandchildren, I was alive in COVID-19, And I'll still be alive, too. I'm going to be alive 100 years from now. I'll only be 146, so I'll still be looking good, Anyway, suppose a flu-like virus is spreading through a population of 500,000 at a rate proportional to both the number of people infected and the number of people uninfected. So this is exponential. This is logarithmic growth. You have the number of people infected and the number of people uninfected. If 100 people are infected yesterday, 300 people are infected today. So again, yesterday is now my time 0. Yesterday is 0, 100. Then what is today? Today, right, is 1, 130. Okay? Because they're going to ask you in part B, determine how many people will be infected a week from today. So a week from today is what time value? A week from today. Today is 1. What is a week from today? Hint, hint, hint. So part A, write an expression for the number of people N of T infected after T days. So if you think back to what we just learned about squirrels, right? I could use this same formula right here, guys. use P for population, or they tell you to use N. They tell you to use N, right? N of T. But notice, what is the limiting value? What is like the maximum number of people that that can be infected by this virus? What is the maximum population? The population is 500,000. So your differential equation would be dn dt, or you could call that n prime if you want, would equal kn times 550,000 minus n. That would also tell you a differential equation solution. So I have the answers here. If you want, maybe pause the problem so that you can try this on your own. Here's the differential equation. dn dt, or n prime, is k times n times 50,000 minus n. So what I ask you to do now is write the equation for n of t. We know an equation for n of t because remember, it's a divided by 1 plus c e to the negative a k t power. You have the equation written up above. So you pause the video, you work it out, right? Pause the video, work it out. Unpause it, now we're back. Here's the differential equation. Now we have to do like we did with the squirrels. We have 2 points. Notice we have a point that starts with 0. That's important. We have another point that starts with 1. That will help us find the answer to part A. Part A is to write the equation n of t. We have n of t right there in the bottom left corner in green. You all wrote it. What we need to do is find the number for c, and we need to find the number for k, or technically e to the negative 50,000 k. That will give you the equation for n of t. That's part A. Then what you're going to do part B is to plug a number into it. Still haven't told you what number to use, but hopefully you can figure out if today is 1, what number is a week from today? A week from today would be like 1 plus a week, which is how many days? So 1 plus. So I'm going to pause the video, pause it. You're going to work the rest of it out. So it's paused. Okay. I'm going to show you the answer. So if you haven't paused yet, you need to pause it now. Unpause. Now pause it. Okay, now what you're going to do is work it out, and then you're going to pause it. And then after a while of working out, then you're going to unpause it. Okay. So right now I'm going to tell you to unpause it. Okay. We're unpausing it now. Good. So here's the answer. That is my equation in the bottom right corner for n of t. That is the number of people infected by this virus over time. How many people are infected by the virus a week from now? So again, this begs the question: would you rather lock everything down and try to keep the spread slow, or just let it rip? You know, it makes you wonder. Like, what if back in April of 2020 we just let it rip? It was actually March. It was March of 2020, right? What if we just said let it rip? Would we have more deaths? We have 500,000 deaths in this country. Would it be 10 million deaths? Would it be a million? Like, how much are we willing to sacrifice? Like I don't really want 10 million people to die, but like 1 million is not so bad, right? Like, where do you all draw the line? I don't know. To me, the answer is no one dies, right? So think about it. If we had all locked down and not gone anywhere and always wore masks even while we were kissing our wives, right? Then hopefully we would only have 1 or 2 people die, right? So, how many people died after a week? Actually, this is not a question of dying. This was a question of infected. So this is a virus that infects people, but no one dies. How about that? So if I plug in 8, 8 is a week from today. 1 plus 7. Oh, it's down here. 1 plus 7 is 8. Then I got 806 people. Anyway, all right. This is a long video. No one's gonna watch it. Daggone it. Oh well. I had fun talking to myself. I love you. Bye.